Hey there, this is notes number 13, volumes of known cross sections, okay? Go ahead and write down the FLT here. Make sure that you guys have your graphing calculator ready, okay? So a very straightforward FLT here. You're going to be given a function or functions, and you're going to be asked to finding the volume with known cross sections. So it's a different type of volume here. And the first task that you really want to accomplish is understanding how the volume is built, how this three-dimensional shape is built, okay? Even though you're not asked to sketch it, you want to know the logic behind it there, okay? And then once you get an idea of what the visual is, then you can work on, well, how do I calculate this, right? Okay, so in the last two lessons, when you guys were learning the disc and the washer and the shell method, it involved a revolution. That's why we called it volumes of solids of revolutions, because you're spinning this shape so that you get a volume of revolution, right? So it's a circular spinning that created this three-dimensional shape. Well, in today's lesson, there is no spinning involved, okay? So let me give you an idea, and then I'll kind of dabble with Desmos for you guys to kind of give you a better visual. But let's say that you take a look at this pyramid, right? Notice how if you had, let's call this cake, right? You had this cake in the shape of a pyramid. If you were to slice it vertically, right from the, I believe it's called the apex, all the way down to the bottom, notice how that cross section is in the shape of a triangle. Okay, the cross section is pretty much what do you see if you were to look at it from the side, right? Now, if instead you were to slice it horizontally, like in this picture, if you were to open that up, that cross section would be in the shape of a square here. Okay, so cross sections could be of many different shapes. So just to give you another visual, if you guys had a can, but let's call it cake, and you were to slice it right here, that will open up and give you a circular cross section. Okay, the face of it would be a circle. So what do we do if we know the cross sections, right? What kind of shapes can we make? So let me give you an example here. Let's say we had a pyramid and we were to lay it down on its side here, okay? If I were to slice it many times this way, what would the shape of my cross sections be? Think about that there for a second, then press play when you're ready. So here, if you were to slice it vertically with this orientation, you would get a bunch of squares, right? You would have like a lot of different shapes of squares. It's kind of like slicing bread, right? So I want you to think about that. Let's say we were to focus on just one of these squares, right? Now, it's still three-dimensional because it has a little bit of a width to it. So it actually is a prism, something like that, right? A slice of a bread. So it's still three-dimensional, okay? Because it has a little bit of a thickness here. So think about that. That one slice is right here, okay? And it's on the surface. If you take a look at the bottom, it's on the surface of this shape here that's kind of triangular. All right. So visualize this. If you were to stand up here and you were to look downwards, this is exactly what you would see. This is called our bird's eye view. So if you were standing at the top of it, you're looking down, that red prism now looks like a rectangle because you're looking directly at the top of it. Okay? And the surface is that purple region right there, or blue, whatever you call it. So, in theory, if I can find out the volume of this one slice, I can use calculus to find the volume of every single slice that I have here, an infinite amount. So here's what you do. Basically, it's the area of your base, and we're going to integrate it. And that's it. Because think about it, this one slice here is really just the area of the base times the thickness times the height. So in this case, the height is just your delta x, the thickness, right? The area of your base is just length times width in this case. Now, if you want to squeeze in an infinite amount of these prisms, you can integrate it, but the delta x turns into dx because you're squeezing in an infinite amount. And down here, length times width for this square is really just the area of the base, okay? So what if it was a different shape, right? And we'll talk about that, but this is pretty much what you want to have jotted down. We're pretty much taking the integral of our area, okay? The area of the base. Now, the cross section will change in shape. So I'm going to show you that in this illustration here, okay? So I know there's a lot going on, but basically you have a parabola here, a horizontal line, and what we're going to do is we're going to go ahead and put a bunch of semicircles as the cross section, okay? So right now here, if I were to increase the number of semicircles, you get the shape here, but notice how that doesn't really show you what it looks like, right? So let me go ahead and kind of tilt this a little bit so that you can see. Let's see, let's go this way. So notice how if I change my perspective, I'm looking at this a little bit sideways here. Let me tilt that a little bit. You'll see that cross section, that semicircle that's in orange there, okay? And if I squeeze in an infinite amount, you'll notice that it starts to develop a more smooth or smoother three-dimensional shape. Right here, it looks like an empanada or a dumpling. I don't know what you would call this, but notice it has more of a three-dimensional shape here. But what I do want to note to you guys is that the bottom is flat. So we're not revolving this like the last lesson, okay? So notice how the bottom is always flat here. So with volumes of known cross sections, it's a little bit different. The bottom is always flat, and you're just stacking a bunch of semicircles, in this case, on top, okay? So let me go ahead and try to put this back to normal so that you guys can see it. Oh gosh. I always get dizzy when we deal with this. Okay, there we go. So that's somewhat a bird's eye view. This is what you guys would normally see, okay? Now, what if I were to change it to a triangle? Okay, so let me pause this for a second. So right now, if I were to just tilt it this way and give it a little bit of an angle, you'll notice that with a triangle, it kind of gives you, oh gosh, what shape would you call this? Yeah, I don't know what you would call this. Yeah, I don't know what you would call it, okay? But you guys can see that. But most importantly, it's still flat at the bottom, if you guys noticed there, okay? Now, what if I were to make my cross-section a square, okay? So notice how it's slightly different each time. Yeah, to be honest, I wouldn't know what you guys would call this, but as you can tell, you could kind of create whatever shape you want, but depending on the cross section, it's a little bit different each time. Okay? Notice how when I create a pentagon, it goes a little crazy there, right? But anyways, you guys get the idea. if you change the size or change the shape, notice how it changes significantly, right? That's kind of what Dr. G would say, gnarly, right? But notice how that bottom is still flat. Okay, so just keep that in mind. Anyways, here we go. So really it boils down to the integral of the area of your cross section. Don't forget that, okay? So here are some common, I guess before we get to that, here are some common shapes that you guys should definitely know. It's okay if you forgot, but these are the ones that are used on the AP exam. So for instance, you guys should know that area is just whatever your side is squared. A rectangle, we should know, is base times height, or in this case, length times width. A semicircle is pi r squared divided by 2, because semi means you cut it in half. So semicircle is pi r squared over 2. So a quarter circle is really just pi r squared over 4. So these 4 formulas right here, you guys should definitely be very strong in, okay? These two are just very special, specific triangles here, okay? So don't forget that area of a triangle is 1/2 base times height, okay? Now, for an isosceles right triangle, that means that these two sides are the same. So if those two sides are the same, it's technically 1/2 base times base, which is the same thing as base squared over 2, which is how we got this. A little bit new, but not really, okay? And here's the last one here. I'll prove it to you guys very quickly for an equilateral triangle, okay? It deals with special right triangles. So here you know the base is just b, right? The height we don't know. So what happens here is if you just look at just one side of that triangle, down below here is just b over 2 because it's half. The height here is just dealing with a special right triangle. This is a 60 degree because it's equilateral. So this must be 30. So if you guys remember anything from pre-cal or integrated math 3, don't worry if you didn't. The 60 degrees is the same thing as whatever the opposite of 30 degrees is, but with a radical 3 in front of it. So the height there is really radical 3 over 2b. And again, you're not going to be asked to derive this, but I just want you to see where it comes from. That's radical 3 over 4b squared, which is what we have here. Okay? So anyways, that's just a very quick proof. Refer to it if you forget, but don't worry. Don't worry so much about the derivation of each formula here, okay? Just make sure you know it, all right? Okay, so some phrases that you want to remember, okay, before we actually do all the problems. They'll always mention that these cross sections are going to be perpendicular to either the x-axis or the y-axis. Very easy to remember. So if they state that it's perpendicular to the x-axis, you integrate with x. Very straightforward. If it's perpendicular to the y-axis, it's with respect to y. All right? So here we go. Okay, so here, go ahead and write it down. Press play when you're ready. Okay, so here the first thing you want to do, just like all of the other lessons, you want to draw a picture, okay? So here, we have two linear functions. Okay, y equals mx plus b. You should be able to sketch that by hand, but if you forgot, refresh, okay? So for instance, this first one here has a y-intercept of -1, and then we're going to rise 1 and run 2 from that point. So our first line is that right there. Our second line, I'll do in purple, has a y-intercept of +1, and then we're going to rise down 1 over 2, It looks a little bit like that, okay? X equals 0 and x equals 2 are two vertical lines. X equals 0 is really just the y-axis, and x equals 2 is really just that vertical line right there. So notice how there's a region, okay? This is the flat bottom. This is where you're going to lay all of your cross sections, okay? So here's what you do. First, you want to note that it says it's perpendicular to the x-axis, okay? So that just tells you that we're integrating with dx, okay? So right away, what you're going to do is you're going to draw a sample rectangle. Remember, dx means we have a vertical rectangle, okay? Okay, so what you're going to do here is we're going to show that that one cross section represents, in this case, squares. So I'm going to draw a square here, okay, as a sample. Okay, so here's what you do. This highlighting is very important here. Let me use pink. So this length right here, the length of this rectangle is really the bottom part of this square. Okay, so you're stacking a bunch of squares on top of this flat surface. Okay, so here we go. V will equal the integral of from a to b of the area of your base dx. Your region starts from 0 all the way to 2 because that's where your region starts and stops, okay? The area of your base, since we have a square, you know it's going to be something squared because that's the area of a square here. To find the length of that square, that's like trying to find the length of that purple rectangle, okay? How do you find the height of that? So that's really just top. In this case, it's negative. I'll put more space here. It's negative 1/2 x plus 1 minus the top, which is the bottom, 1/2 x minus 1. All of that is being squared. Top minus bottom gives you the length of that one side. And since it's a square, it's something squared, dx. Okay, now a few things before we move on. You could definitely use y1 and y2, okay? Now, for the AP exam, if you're going to write down y1 and y2, like for instance, if you were going to write the integral from 0 to 2 of quantity y2 minus y1, you can do that, but remember, the AP reader does not see your calculator. So if you want to write this text here, you have to somewhere declare let y1 represent 1/2 x minus 1 and y2 equal negative 1/2 x plus 1. If you do not declare it, they are not going to know what you're talking about, and they're not going to guess, okay? So you could use the shortcuts, but you have to declare it, okay? Because they're not going to know what's y1 and y2 on your calculator, okay? All right, anyways. So you plug and chug, and you get your answer, okay? I'm going to go ahead and type this in. We'll do this first one together, and the rest I'll just leave it up to you guys, okay? So I'll make sure that y1 is 1/2 x minus 1, and y2 is negative 1/2 x plus 1. Okay, when you're at your home screen, you should go to Math 9 from 0 to 2. And we're going to have parentheses alpha trace of y2 minus alpha trace y1. I know I'm moving a little bit fast here. Squared dx. But you guys have seen calculations before, so it's just a matter of you going at your own pace there. You should get 2.667. Now notice outside there is no pi or 2 pi because we're not using the disk or washer. We're not using the shell method here. And more importantly, we're not revolving. We're not spinning the shape. Okay? Okay, so there's your answer, right? Just so you get a better idea of how things would change up, we're going to do very similar problems here. So I'm going to go ahead and let me see if I can duplicate this. Do I need to duplicate it? Let's try. Okay, so here's part B. Here's what I'm going to change up for you guys, okay? So what I want you to do now is I want you to draw the picture one more time, okay? We'll still keep y1 and y2 on our calculators just to keep it simple. Part B here, I'm going to write down that the cross section is, let's do a quarter circle. All right. So now, instead of squares, it's a quarter circle, okay? So I want to show you how it's different. So make sure that you have a brand new picture, okay? Because I want you to get used to it. What we're going to do here is we're going to go ahead and draw that sample quarter circle. Kind of looks like a shark fin, okay? So same idea. This pink highlight, the top minus bottom, is really this right here. You're stacking a bunch of shark fins at the top, okay? So here we go. V equals, we're still going from 0 to 2, but the shape of the cross-section changed. We're dealing with a quarter circle. A quarter circle is pi r squared over 4dx. Notice how I put that in right away. That is a quarter circle, okay? Now, the radius, pi r squared, the radius is right here. Now, how do I get the length of that orange highlight? That's really just top minus the bottom here. So in this case, it's really just y2 minus y1. Okay, so if your cross-section changes, the area formula will change too, obviously, right? So there you go. Now when you chug, notice how the pi over 4 is just a coefficient. You could actually scoot that to the outside so that when you type it into your calculator, it's a little bit easier to do, less likely that you'll run into any calculational errors, okay? So I'll type this one out with you. This is going to be pi over 4, okay, times math 9 from 0 to 2, and we're going to do alpha trace y2 minus alpha trace y1, all to the second power dx. And this is really just to make sure that you guys are punching it in correctly. You should get 2.094 if you round it correctly. Okay, if you didn't, just let me know. Okay, let's do a part C. So now, part C, let me go ahead and change up the cross section here. Okay, so in part C, and you guys can draw the shape one more time, okay? It's important that you guys do. It's good practice. Part C here, I'm going to call these semicircles. Okay, so in this case, you get like this half circle. This really narrow, like taco shape, if you will. Okay, so the reason why this picture is so important, you'll see in this example, okay? So the pink highlight right here in this rectangle is really the pink highlight here. You're stacking a bunch of these semicircles on top of this blue region, okay? Now I want you guys to pay attention to this here, okay? Fill out everything first in general. So we know that this is the integral from 0 to 2 because the region still starts from 0 to 2. I know that this is dx. Since this is a semicircle, I know it's going to be pi something squared over 2. Okay? Now, what's supposed to go in here is the radius, pi r squared over 2. Make sure you guys focus on this problem. It's almost always on the AP exam, okay? How would I get the radius? So notice how this right here, if I did top minus bottom, will that represent the radius of that semicircle? Okay? Notice how that highlight goes all the way across over here, right? That is actually the diameter. So when we say y2 minus y1 in this picture, that's actually the diameter. But what we need is the radius. So how would we find that, right? So this right here, the radius is always half of the diameter. So you know the radius is really just y2 minus y1 all over 2. Okay? So look, people tend to flip out because there's so much going on right here. So here's what I encourage you guys to do. All right? You're going to go to your y equals. So right now, your y1 and your y2 are already declared, okay? To make things easier, what you're going to do is you're going to go down to y3. Okay? And here's what you're going to type. y3 is going to represent our radius. So we're going to type parentheses y2 minus y1 closed divided by 2. Okay, and I'll show you how this is beneficial. Some of you may have already seen it. So we're going to write parentheses alpha trace y2 minus alpha trace y1, close it, divided by 2. So right now on your calculator, y3 represents our radius, okay? Here's what this does, and we're going to declare it too, okay? When you go to your home screen, you can type it out a lot easier, okay? So here we go. V equals this pi over 2 out here. I'm going to go ahead and scoot it outside. Okay? Integral 0 to 2. And the radius, I can call that y3 squared dx. Here's a reason why we do that. It's a lot easier to type. But also, people tend to get confused with keeping track of everything. The 2's is really what throws people off. The 2 down here is what made it a semicircle. The 2 in here is what we needed to do to get our radius. Two very different things, okay? But if you declare it, you won't run into that problem. So here we go. If you type this out, we have pi over 2 times math 9 for integral. We're going to go from 0 to 2. And we can just say alpha trace y3 squared dx. You should get 1.047 if you round it correctly, okay? Chances are, if you were to try to write this out, you're more than likely to get a syntax error or a calculational error there, okay? So take advantage of the copy-paste idea, okay? Okay, remember, this one was a little bit different because the top minus bottom did not give us the radius, whereas in the last example, quarter circles, top minus bottom gave us the radius. So make sure you guys pay attention to that one, okay? I'm going to go ahead and do one more with you guys. We'll copy paste this one here one more time. Okay, I'll deal with one more shape just to make sure you guys get the idea. Here's part D. I'll erase all the unnecessary stuff. Shoot. Okay, we're going to draw the picture one more time. But now I'm going to tell you that the cross section, here's part D, is a rectangle where the height is 5 times the base. Okay? The height is a rectangle where the height is 5 times the base. Okay, so here we go. I'm going to draw a sample rectangle. Actually, just to be a little bit more accurate, the height is 5 times the base. Okay? Not to scale. So that pink line, the height of that is really just the base of this. It's always the base because you're stacking a bunch of rectangles on top. Okay? So here we go. Volume is equal to the integral from 0 to 2. The region didn't change. Now, since this is a rectangle, this is really just the base times the height. I'll write it right above so we can see it. Now, in order to get our base, which is really the pink highlight, that's just top minus bottom. So in this case, y2 minus y1. Now, how do we get the height, right? The height of the rectangle that we're stacking is going to be 5 times the base. So if you know that the base is y2 minus y1, then the height will be 5 times that. That's it. They'll always tell you what the other side is, okay? For rectangles at least. Okay, so if you clean this up, before you calculate it, it should be a little bit easier. That 5 you can scoot outside. And since the two quantities are the same, that's the same thing as y2 minus y1 squared dx. You could just plug and chug there, and I'll let you guys figure that one out. Okay? So that's really it. The formula in general is the same, but the area, it depends on your cross-section. All right? So let's do one more. Where are we? Let's do this one. And we'll end it for the day, okay? So I provided the picture for you guys. Draw it out. Okay, so some things to note. Perpendicular to the x-axis, remember that just means that we're integrating with dx, which is why we have a vertical rectangle here. You always want to sketch what the cross-section is. So they stated that they were semicircles. Okay, so that means that the yellow here is really the bottom of that semicircle there. Okay, so here we go. V equals the integral of the area of a cross-section. Okay, so area of a semicircle is going to be pi r squared over 2. So I fill out the important stuff first, okay? The region starts and stops. Now, they do tell you, but you could actually find the intersection on your calculator. But here, they tell you that it's going from -2 to 2. Okay? Fill out your radius here. Press play when you're ready, okay? Okay, so I am going to let y1 be x squared and y2 be 8 minus x squared. So that way, it's a little bit easier. So I know that y2 is the upside down parabola and y1 is the right side up parabola, okay? So in this case, top minus bottom is really y2 minus y1. But that right there is your yellow highlight, which is really your diameter. So to get my radius, I need to divide all that by 2. That is my radius. Okay, which I'll let y3 represent because I want to make sure that when I type this out, it's easiest for me, okay? So this is really just y3. So actually, I could scoot out that pi over 2 to the outside. So that would just be v equals pi over 2 integral from -2 to 2 of y3 squared dx, okay? Type that out there. Okay, so y1 is x squared. y2 is 8 minus x squared. Make sure that you guys are not using the old y1 and y2 from the last example, okay? y3, I'm going to let y parentheses y2 minus alpha trace y1 close divided by 2. Okay, so I have pi divided by 2 times math 9 from -2 to 2. Make sure that you guys are using the negative symbol, not the minus symbol. Alpha trace y3 squared dx. Okay, now if you have the old school calculator, let me know. It shouldn't be that much different though, okay? You should get 53.617 if you round it correctly, okay? Now, if you didn't get that, just let me know. Okay, that's pretty much it. So the only thing different is what your cross-section shape should be. But I encourage you guys, please, this is the most important part. Draw the shape out and highlight what top and bottom gives you because that tells you everything there, okay? That's pretty much it. All right, text me if you guys have any questions. Other than that, go ahead and start practicing, okay?